In this problem, the goal was to determine the mass of a black hole, which was being orbited by a star of known mass. Using Python modeling methods, it was determined that the mass of the black hole was 2.595 times 10 to the 31st kilograms. To find the mass of the black hole, the following equations were used. The magnitude of the net force is equal to the negative universal gravitational constant times the mass of the star times the mass of the black hole over the distance between the star and the black hole squared. So rearranging this equation, we get the second equation, which uses the same exact values as stated above, but will give you the mass of the black hole, or M2. So all of the following values were given or known or determined by the Python modeling method. And Fnet was calculated because we know that because of the momentum principle, delta P is equal to Fnet times delta T. Rearranging this, you find that Fnet is equal to dP over dt. And we know that dP is equal to the final momentum minus the initial momentum, which is also the mass times the final velocity minus the initial velocity. So all of these equations were modeled in Python. Here. Starting with the initial velocity. So the velocity was calculated by taking the position of one spot minus the position of the spot it was in before and doing that over delta t. So here the initial velocity vector and final velocity vectors were created using the method just shown above. And once that was known, we could find the initial momentum and the final momentum by multiplying the initial velocity times the mass and the final velocity times the mass. So that's delta P was calculated. As stated before, Fnet was equal to dP dt, which was equal to delta P over delta T. So Fnet was calculated through this method. Then if you run the module, the final net force is printed, so you can plug this in to the equation just shown. And the final star position is also given, so you can also plug this into the equation to find your value for m, which can be seen that my value was correct because WebAssign said it was. Okay, so there are two different components of Fnet. There's Fnet parallel and Fnet perpendicular that sum to give Fnet. Fnet parallel is equal to the magnitude of P final minus the magnitude of P initial divided by delta T, all times P hat, which is the unit vector of the momentum. So this is equal to Fnet parallel. To calculate Fnet perpendicular, it was known that Fnet minus Fnet parallel would give you Fnet perpendicular. These values were represented on the motion tracker by the following arrows. So the black arrow is equal to Fnet, the blue arrow is equal to Fnet parallel, while the red arrow is equal to Fnet perpendicular. Fnet and Fnet perpendicular point in the same direction towards the center of the circle. Fnet points in the direction of the motion when the object is speeding up, and in the opposite direction when the object is slowing down. So we also know that Fnet is equal to delta P over delta T, Fnet parallel is equal to dP dt parallel, and Fnet perpendicular is equal to dP dt perpendicular. So all of the arrows would point in the same. All of the arrows of dP dt would point in the same direction as their respective Fnet counterparts. But these values still are different, though. dP dt is only a mathematical value, while Fnet is the sum of the forces acting upon the object. Fnet parallel is the rate that the speed changes, while dP dt parallel is only a mathematical value again. And the same is true for Fnet perpendicular, where Fnet perpendicular is equal to the change in direction. So what if, could there be a different mass for the given black hole? Well, if we look at our equations, they're only based on the mass of the black hole is only based on the Fnet, and the distance between the star and the black hole over the mass of the star times the gravitational constant. If none of these values are changed, then there cannot be a different value for the black hole, which means that there's only one possible value for the black hole, which was already found.